Okay, so today we have the integral of cosine ln x dx, and this question tells me to make a substitution and then use integration by parts to evaluate. So firstly, we know that the integral of cosine x dx, well, this is just going to be sine x plus c. Okay, but because this angle is ln x, well, it's going to take more work than that to solve this. So in other words, ln x is the problem area. And with problem areas, well, we're going to say let k equal ln x, because we're going to have to apply integration by parts, and we're going to have to use the variable u anyways. And you could use any variable, you could use t, z, or whatever. Okay, so now we're going to take the derivative, so that dk is going to be 1 over x dx. Okay, now we solve for dx and multiply both sides by x so that you get x dk. Now, we can't really have an x in our new integral after we make the substitution, because we're going to have k, and that's going to be a problem. So we're going to have to replace this x. And if we look here, well, if k is ln x, well, I could raise both sides by e, and because this is an equation, this is valid because we do it on both sides. So that means that e to the k is equal to e to the ln x. This cancels out, it becomes x. So this implies that dx is just e to the k dk. And now we are ready to make our substitution. So the integral of cosine ln x dx is going to be equal to what? It's going to be equal to the integral of cosine k e to the k dk. And now we are ready for integration by parts. Now, I'm not going to go over the formula for integration by parts because I did do that in the previous video, but I did say that the rule of thumb for picking u is so that we reduce a power. But in this case, take the derivative of e to the k, does not reduce anything. Take the derivative of cosine, it's a trig function, does not reduce anything. So we are stuck, and there is a trick to these types of integrals. So because we are used to taking the derivatives of trig functions, and it's a bit easier than taking the integrals of them, I'm just going to choose u to be cosine k. Now you could choose u to be e to the k, and this will work out perfectly. So as long as you choose the same corresponding u and dv values, and I'm going to show you what I mean after we apply the integration by parts. But this is just personal preference, you could choose anything. So because we chose that to be u, that means e to the k dk is going to be dv. Now this means that du is going to be minus sine k, and that means it's going to be dk, and that means that v is going to be e to the k. Now we can apply integration by parts. So this integral is just going to be equal to, so what does it say? It says u times v, which is just the same thing as v times u, so I'm going to write it like that, minus the integral of v du. Okay, so v du is e to the k times minus sine k dk. Now what I'm going to do is I'm going to pull this minus sign to the front, and what that's going to do is make this positive. Now if you've noticed, it looks like we haven't made any progress at all, and that is not true because we are basically halfway done. Okay, the last thing to do is apply one more integration by parts for that integral, and then we will be done. So again, this whole integral cosine k e to the k dk is going to be equal to, actually I'm not going to write that yet. Let's pick our u and dv. So u dv. Now what I meant earlier was, well, if you pick the u to be a trig function, then please pick u to be the trig function here. Okay, it has to be corresponding for this to work. So since we picked dv to be e to the k, that means we pick dv to be e to the k again. Okay, that's perfect. So that means du is going to be cosine k dk, and that also means that v is still going to be e to the k. So now the same integral that we have above is going to be equal to, we copy the first part down, so e to the k times cosine k, now plus, now you put our brackets, we apply the integration by parts, so u times v, I'm going to write it as v times u, it's the same thing, minus the integral of v du, and I'm going to write it as du times v. Okay, it's the same thing, and then dk. Okay, so that's looking good, that's looking good. So because this is a plus here, we can drop the brackets, not really going to change anything, so that's going to stay the same, and this is also going to stay the same. Now why would I do integration by parts twice? Well, if you notice, this is supposed to be the same integral here, and that's why I kept writing it, so that it becomes clear that, well, we have this integral here, and then ooh, this is the exact same one, and there's a minus sign. So what does that mean? That means that I can add them to both sides, and what would that give me? 2 of the same integral. Okay, I added the same thing to here, so I get 2 of them, equals e to the k cosine k plus e to the k sine k, and then now we divide by 2 to get rid of that. So dividing by 2 is the same thing as multiplying by a half. That looks ugly, so I'm going to rewrite that. We are multiplying the whole thing, so put the brackets. Now the last thing to do, of course, is to sub back in for k. Now if we do that to this one on the left hand side, we are going to get our original integral. So it's the integral of cosine ln x dx. So the integral of cosine ln x dx half into e to the ln x cosine, oops, that's not supposed to be k, ln x plus e to the ln x sine ln x. Now, as I said earlier, e to the ln x, these are going to drop down and it just becomes x. So again, we have half x into cosine ln x plus x into sine ln x. And now what I would do to make this just look better is factor out the x. So we get x over 2 cosine ln x plus sine ln x. And looks like we're done, so we can add our plus c. And that is the final solution for this integral. And if you need the whole solution, I'm not sure if I could fit this, but yeah, there you go.